Welcome everyone. My name is Asif Ahmed, Assistant Professor at State University of New York, Sony Polytechnic Institute, and with me,
I'm Mohammad Sadiq Khan, Assistant Professor, Jackson State University.
we are the session chair and co-chair for this session. This session is titled Roadways. We'd like to thank Tensor for generously sponsoring this session. We greatly appreciate their support. A couple of things to note before we start the presentations. You'll have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your questions will be sent directly to the presenter to answer as soon as they are able.
To claim PDH credits for this session and any other education session, you simply need to click on Claim Credit button on the conference homepage. From there, you'll fill out the survey for any session that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend the session and ensure that you receive the proper credits. Please enjoy the presentation.
Enjoy it.
Howdy. I hope that you all are having a wonderful virtual conference experience. The topic of today's presentation is Depth of Influence of a Viking Geotextile Below the Flexible Pavement Constructed over Expansive Subgrade. I am Nirpajyoti Biswas and I am currently working as a PhD student at Texas A&M University College Station under the guidance of Dr. Anand J. Pupala. I would also like to express my gratitude to all the other contributors of this paper, MD Ashrafuzzaman Khan, Dr. Sayantan Chakravarti, and Dr. Surya Sarat Chandra Congress. The presentation outline is shown below. It includes introduction, then I would be touching base with design, construction, and instrumentation. Thereafter, we will be seeing the effect of wicking fibers on subgrade moisture, which includes a depth of influence and subsurface moisture analysis. Finally, we will be seeing the effect of these wicking fibers on pavement deformation, and thereafter we will be concluding this presentation. Here we can see some of the common problems associated with expansive soils. On the top, we can see a failed road embankment in Paris District, Texas. This is from one of our project locations where the failure is mainly attributed to the expansive soils. Below it, we can see cracks developed on building walls, which is quite a common sight in the regions of expansive soils. Additionally, the basement of the buildings are also affected due to the soil pressure of this kind of soils. On the bottom right, we can see the pavements which are built on expansive soils suffers from rutting, cracking, and differential heaving due to the soil shrink behavior of the expansive subgrade over the time during its serviceability. Now, let us discuss in details some of the major problems of pavements built over expansive soil in Texas. These soils are characterized by high plasticity indices and major swelling and shrinkage potential. On the right, we can see that when water migrates into these soils during rainfall, they undergo heaving. Alternatively, during summer months, when they dry up, they develop potential surface cracks. These problems affect the long-term performance of the pavements. As a result, these roads need regular maintenance and substantial cost is involved in maintaining such pavements. Texas Department of Transport Pavement Manual recommends certain measures to deal with such problems, which includes chemical stabilization with lime, cement, and other kind of traditional and non-traditional stabilizers, replacement with superior quality geomaterials, which is not always a suitable option for some locations, and utilization of geosynthetics. However, the cost of using geosynthetics with virgin aggregates may increase the overall project cost, and also the use of virgin aggregates is not a sustainable solution to our pavement construction. As a result, in this project, we have tried to look into the effects of using a moderate quality base material known as reclaimed asphalt pavement aggregates, or RAP aggregates in short, in combination with a newly available geotextile and their effects on the pavement performance. In the present scenario, the use of recycled materials could provide us with long-term sustainable solutions. In an estimation by National Asphalt Pavement Association, we have 102 million tons of RAP aggregate stockpiled all over United States. In Texas, we have fair share of stocked RAP aggregates which the TxDOT plans to recycle and reuse instead of virgin aggregates. On the right, we see a picture of one of the such stockpile from where we collected the RAP aggregates for our laboratory studies. A newly available wicking geotextile, popularly known as H2RI, has been used in this project. This geotextile has a special hydrophilic and hygroscopic deep groove fibers which is capable of draining out moisture in an unsaturated environment through suction. This single geotextile layer can perform multiple functions. In addition to the traditional separation and reinforcement function, this geotextile drains out moisture from pavement layers through capillary action rather than only gravity drainage. This figure shows the schematic diagram of our test section. The test section is located at FM 1807 Venice, Texas. It could be seen that this location predominantly sits on a high expansive zone as seen from the map. This location was chosen because of its history of pavement failure through cracks and ruts even after maintenance by the TxDOT maintenance crew. The eastbound lane has been used as a test section, whereas the westbound lane was used as a control section. The test section consists of a subgrade soil which is expansive in nature, followed by a 15-inch base course of RAP aggregates. The wicking geotextile was installed in between the base and the subgrade layer. The surface layer consists of a 2-inch asphalt overlay. The test section was installed with a number of sensors as shown in the figures below. The shape array accelerometers were used for measuring the vertical deformation below the wheel path. The pressure sensors or earth pressure cells were installed to monitor the stresses at top of the subgrade, and the moisture sensors were installed to monitor the moisture redistribution pattern below the pavement layers. The design of the test and control sections were performed using a standard design software recommended by Texas Department of Transportation known as FPS-21. FPS-21 is a mechanistic empirical design procedure that uses a performance model based on the degradation of the serviceability index as defined in the AASHTO road test research. The material properties of the pavement layers, the traffic loading, the change in serviceability rating, and the desired level of reliability are then used to compute alternative structural designs using FPS-21. The modulus of the subgrade for the reinforced layer was obtained by multiplying a modification factor as obtained from Lin et al. 2019. The design parameters such as annual average daily traffic, average traffic speed, and percentage trucks are shown in the bottom right corner. The plot on the right shows the influence of the wicking fibers in improving the equivalent standard axle load and the structural number of the reinforced layers by the inclusion of a hydraulic improvement factor. This factor was obtained based on a study from different locations in and around United States and Canada. Using the design data and the hydraulic improvement factor, A software listed on the manufacturer website was used to obtain the values of this plot. Here we can see some of the steps involved during the construction of the pavement layers. It started with milling of the existing pavement layers, followed by excavation until the desired depth was reached. Thereafter, the subgrade layer was leveled and compacted using both pneumatic and drum rollers until the target density and moisture content was reached. After compacting the subgrade, the geotextile layers were laid on top of it. After laying the geotextile layer, the pavement was again backfilled with wrap aggregates and were again compacted until target density and moisture content was reached. Thereafter, the pavement was kept open to traffic for another 7 days, after which the TXDOT construction crew came back and laid the layer with a prime coat and asphalt layer. After laying the asphalt layer, the pavement was rolled, and finally at the bottom right we can see the pavement after the construction was completed. Effect of wicking fibers on subgrade moisture. Here we would like to focus on an important property of the wicking fibers. Currently, no experimental studies exist which indicate the influence zone of the wicking fibers. Therefore, in this paper, we tried to introduce a preliminary concept for the estimation of the zone of influence up to which the wicking fiber has an ability to remove moisture in a fine soil subgrade. In the past, some numerical studies have been done by Lin et al. For predicting the zone of efficacy of wicking fibers below and above the geotextile layer. However, they were mostly related to a different coarse-grained material. They indicated that the wicking fibers has the ability to drain out moisture as far as 3 feet from the fiber layers. They also noted that the primary efficacy of the wicking fiber to remove moisture reduces significantly beyond 15 inches from the geotextile layer. Additionally, they also observed a small reduction in moisture content could significantly increase the subgrade modulus. Now we will try to look into the subsurface moisture conditions below the test section after a rainfall event. The moisture sensors labeled 1 to 9 were used to monitor the volumetric moisture content below the test section. The first moisture contour plot on the left shows the moisture distribution immediately after rainfall. The second contour plot shows the condition 5 days after rainfall. The change in the contour colors on the right edge near the pavement shoulder indicates the probable path of drainage of the moisture with the help of wicking geotextile. The plot in the right shows the change in volumetric moisture content for all the moisture sensors below the pavement. It can be noted that the moisture sensor 6 located at 6 inches below the geotextile undergoes maximum reduction in volumetric moisture content. The reduction in moisture is primarily attributed to 2 factors. First, the surface evaporation from the pavement edges, and second, the wicking ability of the geotextile due to the development of a differential suction head between the pavement edges and the pavement center. The moisture sensor 3, which is located at 12 inches below the geotextile layer, also shows significant reduction in moisture content. However, the percentage reduction of moisture content is reduced to more than 50% as compared to moisture sensor 6. The moisture sensors near the center of the pavement showed lower reduction in moisture content during the same period as compared to the edges. However, if we compare the values between moisture sensor 4, which is located at 6 inches below the geotextile layer, and moisture sensor 1, which is located at 12 inches below the geotextile layer, it showed the same trend like moisture sensor 6 and 3. That is, the percentage reduction in moisture content reduced to more than 50% as we move from 6 inches to 12 inches below the geotextile layer. Therefore, from these values, we can observe that the zone of influence of the wicking fiber to drain out moisture extends to about 12 inches below the pavement near the center and even more than that near the pavement edges. After looking into the moisture conditions below the pavement layer, we now look into another important aspect of the pavement performance, which is the permanent deformation. As we have seen in the previous slide, that the wicking fiber can rapidly drain out the moisture from the pavement layer, and this has a direct impact on improving the pavement modulus. As a result of this, the pavement undergoes lower permanent deformation due to combined effect of expansive nature of the subgrade and traffic loads. Also, as the geotextile has a higher tensile modulus property which reinforces the weaker subgrade, and it reduces the stress on top of it due to traffic loads. The combined effect of these factors is visible on the plot shown in the right. The SAA sensors were used to monitor the permanent deformation below the wheel path in the test and the control section. The test section showed lower permanent deformation as compared to the unreinforced control section. The performance of the control section degraded significantly after a heavy rainfall event during the month of May 2019. This indicated the overall efficacy of using the wicking fibers in pavement layers. Also, in the figure below we can see that the pavement surface in the test section shows no visible rutting or cracking after the current monitoring period. Therefore, to conclude, we can say that the wicking geotextile was effective in redistributing the moisture rapidly within the pavement layers after any rainfall event. The efficacy of the wicking fiber was more prominent near the pavement edges because of the surface evaporation as well as the wicking action of the geotextile as compared to the center of the road. The efficacy of the wicking fibers to remove moisture reduced to over 50% at 6 to 12 inches below the pavement layers. However, it should be noted a small amount of reduction of the moisture could substantially increase the resilient modulus response of the pavement, and hence it would affect the long-term pavement performance. Also, a lower permanent deformation was observed in the test section as compared to the control section. Therefore, we can safely say that as of now, the pavement performance has significantly improved due to inclusion of the wicking fiber. We are currently monitoring the pavement performance for another couple of years, and after that, we could provide some design recommendation and guidelines. I would like to thank you all for listening to this presentation. We are happy to answer any questions that you have. Also, I would like to thank our sponsors for supporting this project, includes Texas Department of Transportation, Tenkate Geosynthetics, and NSF's CICI. Thank you.
Good morning, good afternoon, good evening, wherever you are. My name is Prajol Tamrakar and I'm from Tensar International Corporation. Today, I'm going to talk about in situ assessment of geogrid stabilized flexible pavement using automated plate load testing. This paper compares the performances of geogrid stabilized and unstabilized pavement using automated plate load testing or a field testing approach. So let's get started. Before beginning my presentation, I would like to acknowledge my co-authors, Mark Wayne, David White, and Pavana Penapusa. This is the outline of my presentation. I will start from the motivation of the study, then the objective of the study, then I will describe some details of the project, then the concept of base course stabilization and automated plate load testing, then the results, and at the end I will summarize the key findings of the study. Currently, laboratory-based testing methods are usually adopted for the characterization of pavement materials. That is, the materials from different pavement layers are individually tested in the lab and they are used for deriving their mechanical properties. And also during the process of pavement design and analysis, the information from the lab data are used for modeling pavement section and estimating pavement performances. But there are several challenges associated with the lab-based characterization methods. This includes like limited sample size, the lack of effective interaction between different pavement layers, and more importantly, there is no representative boundary condition. For example, ASTO 3307 protocol is used for deriving resilient modulus of unbound pavement materials. Repeated load triaxial testings are performed on a small cylindrical specimen for deriving resilient modulus values for different materials, and the confinement applied in the cylindrical specimen is represented as the confinement that is occur in the field, and the vertical axial stresses are applied in different load frequencies or different stress level to mimic the trafficking condition. But again, although this model or this approach is very advanced, but it still lacks the effective interaction of different pavement layers. In order to get rid of lab-based characterization methods, some field-based plate load tests are also performed by using static or impact loads. Usually a truck or a heavy vehicles or any heavy objects are used for applying loads, and these tests are performed by applying monotonically increasing loads. But again, the challenge in this type of test is that the loads are not representative or not comparable to the traffic condition. Falling weight deflectometer or heavy weight deflectometer are the example of the plate load test that use impact loads. The deflection basins due to the impact loads are analyzed for deriving pavement material characteristics. But the impact load used in this type of testing are not representative to the actual traffic conditions. So we need a different kind of plate load test that uses dynamic loads and that is more representative to the actual traffic conditions. So in this study, we use automated plate load testing that uses dynamic loads. So the objectives of the studies are to evaluate in situ mechanical properties for geogrid stabilized and unstabilized pavement using the APLT system or the automated plate load system. The unstabilized pavements represents the pavements without any kind of geogrid. The another objective is to measure resilient and permanent deformation responses, and the last objective is to estimate pavement model parameters such as composite modulus, layer specific modulus for HMA, aggregate base course, and subgrade. The project site was located near Atlanta, Georgia. The test sections were the part of Interstate 20, and the test sections were located about 30 miles west of Atlanta. There were three sections, Section A, Section B, and Section C. Section A and B were geogrid stabilized section, whereas Section C was unstabilized section or a controlled section. In case of geogrid stabilized sections, the thickness of aggregate base course were reduced by 20 to 40%, whereas the thickness of HMA were same for all cases. And also you can see there were some small differences in the subgrade condition. The subgrade CBR ranges between 15 to 25%. Geogrid stabilized sections were prepared by placing a layer of geogrid at the interface of base and subgrade. A triangular aperture geogrids were used for these projects, and the properties of the geogrid are shown in the table. So let's talk a little bit about the benefit of using GeoGrid by using the concept of base course stabilization. So when a GeoGrid is introduced at the bottom of aggregate layer, it will create different confined zone within the aggregate layer. A layer close to the GeoGrid will be fully confined, and when we move further, the confinement level will be decreased. But in general, a geogrid plus soil will form a composite and strong and stable aggregate layer. So this can be explained by this lateral restraint of the aggregate at the bottom of aggregate. So where the use of geogrid will prevent from lateral movement of aggregate, and this can also be explained by the changing in the shear failure plane by using a geogrid. That is, when a geogrid is used, it will prevent from shear failure of the subgrade. So the base course stabilization will contribute in enhancing the stiffness of aggregate layer and also retaining the stiffness of the aggregate for a longer period of time. So this is a little bit different from the concept of reinforcement. Unbound aggregate layers possess elastoplastic behavior. That is, for each load application or for each loading cycle, the total deformation experienced by the layer will be the sum of permanent and the resilient deformation. So that is, the portion of the deformation will be induced in the pavement in terms of plastic deformation, and the rest will be rebounds in terms of resilient deformation. So we need to understand like how the pavement is behaving due to the repetitive load. The APLT system can measure both resilient and permanent deformation responses from the pavement surface by using precise measurement. In fact, the APLT system is an advanced portable laboratory where a plate load test can be performed by varying different loading conditions such as different loading rate, different load magnitude, and also by using different types of plate. And also in this figure, you can see figure on top right are the example of a raw data. The blue one is the load pulses of different magnitude, and also the red one are the major deformation responses. So we can separate both resilient and permanent deformations from the raw data, and we can analyze this data for further analysis. Figure A shows the APLT system from the actual site, and the figure B shows the loading plate in the center, and there are like 3 additional sensor on top of the arc. So those external sensors were used for back calculating the layer specific modulus. In this testing, the tests were performed in 5 different steps. In all steps, the cyclic stress of 482 kPa is used for applying the cyclic plate load, and the loading frequencies were changed from 2 Hz to 0.01 Hz. And the number of load cycles were also varied. So for the step 1 is 2000, but for other steps it were like few cycles. The permanent deformation responses from the test sections are shown in this figure. So for each test section there are 3 curves. So each curve represents one spot test. So that is, for each test section there are 3 spot tests were performed or 3 APLTs were performed. So deformation response mainly for the step 1 of loading, that is up to 2000 cycles, were used for analyzing the permanent deformation response. So usually the response is gradually increase at the beginning, and after like 200 cycles like it is gradually increasing. But in general, the permanent deformation induced in 3 test sections were very similar, that is like less than like 1.2 millimeter. The resilient deformation measure from the pavement sections are used for deriving this composite modulus. So in general, the resilient deformation represents the composite behavior of that particular test section. Also, the composite modulus is also an indicator of the field performance of that test section. So the figure shows the composite modulus is high when the loading rate is high, and with the decrease of the loading frequency, the composite modulus is also decreased. But when we compare the performances or the composite modulus of different sections, the result shows that the stabilized section with 200 millimeter of aggregate base course has highest composite modulus, whereas the other two sections, what section A and section C, they have like comparatively same or similar composite modulus. The resilient deformation responses under the loading plate are used for deriving the composite modulus, whereas the deformation responses from the other sensors close to the loading plate are used for deriving layer-specific modulus. That is, the concept is similar to the concept of the FWD or SWD. So in this figure, uh, the layer specific modulus for HMA is shown, and it is showing how the HMA modulus is changing with the loading frequency. Similar to the composite modulus, HMA modulus is also changing with the loading rate. For the highest loading rate, the HMA modulus is high, and it decreases with decreasing loading frequency. These are the results for the aggregate base course. The change in the aggregate base course modulus with loading frequency are similar to the HMA modulus or composite modulus. But one distinct thing that we can see from these results is the aggregate base course modulus for stabilized section were higher than that of the unstabilized section, despite the difference in the layer thickness. And one more thing that we can also see is when the loading rate is increased, the aggregate base course modulus is rapidly increased, but such change is not seen for the unstabilized section. These are the results for subgrade modulus. Similar to other measurement, the subgrade modulus is also sensitive to the loading frequency. The results also show that the subgrade modulus for the stabilized section is higher than that of the unstabilized section. So when a geogrid is introduced at the interface of base and subgrade, the geogrid will also have some effect on the subgrade by reducing the stress on it. So that will reflect in terms of enhancing the properties, mainly the mechanical properties of the subgrade, which you can also see from this result. So in summary, in this study, we measure both resilient and permanent deformation responses from geogrid-stabilized and unstabilized pavement using the APLD system. The total surface permanent deformation responses from both sections were sensitive to the loading frequency as well as the loading cycle. The total permanent deformation induced in all sections were very similar, that is, the deformation response were less than 1.2 millimeter. The stabilized pavement with 200 millimeter aggregate base course had the highest composite modulus, while the remaining two pavement sections had a similar modulus. Recall that the composite modulus is a direct indicator of the pavement performance. The back-calculated modulus of geogrid stabilized pavement sections were higher than that of the unstabilized section. Similar to the pavement permanent deformation. The composite modulus were also sensitive to the loading frequency as well as the load cycles. So when you are looking at the back calculated aggregate base force modulus, the rate of change in ABC modulus with loading frequency was distinctively seen for the stabilized pavement and more prominent for the stabilized pavement with 150 millimeter of aggregate base course. That is, when the geogrid is introduced in the aggregate base course, it has like a direct effect, or like the geogrid is directly sensitive to the loading frequency. So these are the summaries from the testing. So one thing that you have noticed is we have just used only one type of uh, loading condition, in the sense like we just use only one stress level. So in future we'll be using more than one stress level, so that would be like more representative to the actual loading condition. So these are the summaries. I would like to acknowledge NGOs for conducting the test, and also Georgia Department of Transportation for allowing us to conduct test in their test section. Thank you. Please let me know if you have any questions, comments, or feedback.
Hello and welcome to our presentation. My name is Tim. I'm one of the authors of this paper, and I'm pleased to present Unpaved Access Road Utilizing Polymeric Geocell Reinforcement over High Water Bearing Muskeg to you today. To start things off, I would just like to thank and introduce my co-authors. Dr. Sanat Pokharel is the principal engineer at Stratum Logics and author of more than 45 research publications. His expertise in NPA geocells was paramount in design and implementation of the project we are discussing today. Mr. Murtaza Ali is a project engineer at Stratum Logics and was one of the field engineers on site for this project. Much of the construction information and many of the photographs we have that we're showing here today is thanks to him. Mr. Mark Bro is the president of Paradox Access Solutions. He is a visionary and one of the best advocates for the inclusion of geosynthetics in construction projects in North America. In today's presentation, I will start with an overview of the project, including its geographic context, some goals and challenges, and characterization of the site conditions. I will then move into the considerations we had during design and describe the materials we selected. And then I will jump to talk about construction, where you can see some of the photos we took. And I'll talk about performance, have some discussion, and show you our conclusions. The focus of this presentation is a project in the province of Alberta, which is in the great country of Canada where I live. The 11.5 kilometer road is located in what is considered northern Alberta. In the sketch on the right here, I've tried to show the project location in relation to one of the more recognizable landmarks in Alberta, Fort McMurray. So it's about 85 kilometers from Fort McMurray. However, access to the site is only available through private roads off a highway near Wabasca, which is a hamlet in northern Alberta. These private roads are frequently used as logging routes. Because this road is in such a remote location, this site in particular was our client's last fly-in and fly-out access. Here's a slightly more zoomed-in view of the access road on the right here. As I mentioned in the last slide, this access road was being built to provide all-season access to our client's last fly-in, fly-out only site. Prior to our involvement, the client would build ice roads every winter in this alignment in order to be able to access the site. And then these ice roads would melt in the summer and they would only be able to access using ATVs or by helicopter. The reason they had not built a more permanent road before is because of the poor soil conditions in the area. Much of the site is covered in muskeg. If you've been to northern Alberta, you'll know what muskeg is like. It's a peat-like substance, high moisture content, fibrous, very difficult to build on. On top of that, the site was in a very environmental sensitive area, and therefore it was of utmost importance to limit the footprint of the permanent road. Our client was also expanding the site and needed to transport some large prefabricated structures. The type of vehicle required to move these structures don't always have the best turning radius, so what we ended up having to do is balance the need to allow turning movements of this oversized vehicle while minimizing our road footprint. Other challenges included making sure the road construction would not impact a small creek and some existing transmission lines, as well as planning the construction sequencing. Due to the fact that the road could only be accessed on one side, coordinating haul trucks on a narrower road had to be managed as well. You'll see here some photos of the site conditions from site visits in 2015 and 2018. As you can see, the site is quite wet. Field investigation program for this project included ground penetrating radar, muskeg depth probing, and dynamic cone penetrometer testing where it was feasible. What we identified from the field program is that about 8 kilometers of the total 11.5 kilometers consisted of very soft muskeg deposits, while the other 3 kilometers had a range of soft to firm clay. The muskeg deposits were as deep as 2 meters in some areas. Shown at the bottom of the slide is a simple sketch showing the presumed depth of muskeg or soft soils found in the field investigation. As you can see, the depth is not consistent over the whole site, which led us to varying thicknesses in design based on the site condition. So in muskeg, one traditional method is to remove all of it and replace it with competent soils. In this project, we did not pursue this process for budgetary and environmental reasons. I don't have the personal experience with such construction methods, but I have had the opportunity to talk to construction managers who have done the traditional method. And what I'm told by them is that one of the additional challenges in this conventional method is when the muskeg is removed, the remaining ground can still be quite uneven and still quite difficult to work with. The alternative design, which is the subject of this paper, incorporated 2 layers of geocell, woven and non-woven geotextiles, and sand and gravel as fill materials. The structure was incorporated into a road cross-section that has 7-meter wide road top and a side slope of 2.5 to 1. This is in comparison to a typical side slope of 4 to 1, which is standard for many road projects. The sharper side slope was chosen because we were intending to reduce the project footprint. The design having steeper side slopes also relied on the presence of geosynthetics to stabilize the fill. The structure was designed to have an appropriate factor of safety against rutting, as mentioned in Pocarel 2010, and against hoop stresses induced by the vehicle loading. Vehicle load considerations included the vehicles expected after road construction, but it also included vehicles during construction of the road, and as I mentioned before, loads for construction of the site upgrades. So here's our design schematic. The top schematic references the structure in areas where there was no deep muskeg, and the bottom schematic shows the structure in deep muskeg. If you recall from a couple slides ago, the muskeg or soft soils depth varied along the profile. So we were able to characterize the differences along the profile and come up with 4 categories, which you see here: 500 meters of dry, firm clay subgrade, 2,500 meters of clay subgrade with moderately well-draining surroundings, 4,500 meters of soft clay and muskeg with a high water table, and about 4,000 meters of deep muskeg. So looking at the sketch here, the construction sequence would be first to install a high-strength non-woven geotextile on top of existing ground, stretch a layer of NPA geocell over it, fill it with sand, and then the sand would have to be placed slowly, and the structure would be allowed to settle until equilibrium was reached. Subsequent sand lifts would then be placed until the desired thickness was achieved. Following this would be placement of the woven geotextile, another layer of geocell, and placement and compaction of crushed gravel. Here you can see a summary of the material properties. If you look at the NPA geocell properties, you can see that I've distinguished between the top and bottom layers of geocell, and it has to do with the purpose of each layer. So the bottom layer is used to confine the sand and prevent shearing of muskeg. So the main loading on this bottom layer would come from self-weight of the fill material, and therefore the stiffness of the geocell does not have as much of an impact. Compare that to the top layer geocell, which needed to be stiffer to increase the total modulus of the pavement structure to prevent rutting. So the increased stiffness of the geocell also helps prevent bursting of the geocell due to heavy traffic loads. For geotextiles, 1,330 Newton non-woven geotextile was used for the bottom layer with 50% grab elongation in order to stretch appropriately as the muskeg settled. The higher grab tensile strength was chosen to increase factor of safety against geotextile rupture. The middle non-woven geotextile was 911 newtons, and the woven geotextile was placed under the top layer of NPA geocell and had a grab tensile strength of 911 newtons. We chose free draining materials for the infill in the geocell, and it was important to keep the percentage of fines in sand relatively low to keep this free draining characteristic. All right, so now we'll show you some photos from the construction phase. Shown here on the left is the bottom layer geocell with a non-woven geotextile underneath it. And on the right, you can see a dozer pushing the fill sand into the geocell. When filling geocells, it's important to make sure that the construction equipment does not simply push the fill material horizontally. Sometimes this can cause the geocell to shift and lose optimal stretch dimensions. So instead, construction equipment is supposed to lift the material as it approaches unfilled cells and gently allow the sand to fall vertically toward the cells. You can kind of see what I'm talking about in the picture on the right, where the dozer blade is slightly elevated above the grade of the material. On the left here, we have a photo of the type of rock truck used to transport the material along the road. As you can see, the rock trucks are quite wide, and so it required careful coordination to make sure these trucks could safely pass one another as they made their rounds. Here's a pro tip if you ever work on a project like this. If you're nice and courteous to the rock truck drivers and you don't have a vehicle on site, I found that a lot of them are friendly, so they're willing to give you a lift up and down the road. Also shown in the left photo is the temporary matted workspace that was set up using rig mats. This temporary matted workspace was important to keep workers safe while the rock trucks and other construction equipment built the road. It was also very helpful for transporting sections of geocell and rolls of geotextile without holding up the material haul. And here on the right, we have a packer or a smooth drum roller compacting the fill material. On the left here is a photo of a water truck adjusting the moisture content of gravel on the road to ensure compaction within a range near the optimum moisture content. You can also see the woven geotextile that was used in the top layer. So ideally, aggregate should be at optimum when brought to the road. However, as this site was very remote, the material had to be stockpiled at another remote site, meaning that moisture control was not that easy. Here on the right is the completed top layer gravel fill. And it might be a little hard to make out, but if you look far in the distance in this photo, you can see a truck parked off the road. So during construction, we also had temporary turnabouts situated every few hundred meters to allow the rock trucks to turn around. This was good as there was not enough room on the main road to do so. I'll speak a bit to the construction sequencing here and just show you some of the unique techniques that were employed in this particular project. So in the first row, the first photo, you can see them laying out geotextile using a combination of equipment and human effort. On the left of that photo, you can see the geocell is hooked onto a nod well. And so as the nod well backs up, geotextile is laid out more and more. In the second photo, you can see the labor effort being used to stretch the geocell in a straight line. And then when you move over to the third photo, you can see the geocell after it's been stretched in place. Moving on to the bottom row, in the first photo, you can see the sand fill has been placed and is being compacted. In the second photo, you'll see that woven geotextile has been laid on top. And For the geocell on top of the geotextile, you can see individual sections snaked out along the middle. So each of these sections will be stapled together and then stretched as a whole, like you see in the third photo down there. The photos shown here are from immediately after construction and after one freeze-thaw cycle. I want to explain the kind of loading that went on the road before the picture on the right was taken. So at least an additional 10,000 tons of granular material were brought on rock trucks over this road to a site at the end of the road. And that was all before we took this photo after one freeze-thaw cycle. As of November 2020, the road has exhibited no operational concerns and is performing to the desired quality. The confirmation of this performance is based on our visual observations from regular users of the road. And these regular users include one of our authors, the contractor's PM, the client representatives. And actually, in the most recent inspection, the road surface has revealed minimal rutting, and there were no instabilities identified in the road embankment. To give you an understanding of the quality of the road, we had some individuals joke about the road being too high quality for a gravel road. Turns out some drivers were encouraged to speed due to how good the condition of the road surface was compared to other private roads in the area. So go figure. As mentioned before, having only one access point to the road was challenging, and it limited our construction schedule. As written here, due to the linear nature of the road construction, constructing a greater length of bottom layer prior to installing the top layer was desirable from a scheduling perspective. The greater length before top layer construction, the more sand composite basal layer was subjected to frequent construction loading from rock trucks. So the geocell reduced stress directed to the muskeg subgrade, allowing for greater lengths to be used while keeping the embankment stable. Now the finished portions of the access road, so that's the front of the access road, were constantly under heavy traffic, as that was the only route of travel. Even with this amount of travel, coupled with the rainy season that the construction team had, the construction crew had to do minimal maintenance when building. Generally based on comments from the construction crew as well as reporting, it was found that our predictions were mostly accurate. There were some deviations, but it is understood that some of it came from increased rainfall as well as clearing of trees, both of which affected the expected water and surface elevations. The accuracy can be attributed to the data we got from field investigation. We found that out of all the sources of data, the ground penetrating radar was the most accurate in predicting site conditions. Probing and the dynamic cone penetrometer were good for shallow information, but due to their short reach, they did not identify the depth of muskeg well. The design was compared to a conventional method for cost savings. As you can see here, we had approximately 600 cubic meters of muskeg removal savings, approximately 2,900 cubic meters of gravel fill savings, approximately 37,550 cubic meters of embankment fill savings, and savings on the cost of aggregate supply alone was estimated to be 66%, and aggregate haul with a 140-kilometer haul distance was estimated to be 77%. It's also worth noting that the fewer number of haul trips and the less aggregate volume are factors that contribute to reduced CO2 emissions. So here's the conclusions. The two-layered MPA geocell design was used as an alternative to the conventional method of removing and replacing muskeg with competent fill, which resulted in a reduction in aggregate volume of approximately 66% and reducing CO2 emissions by approximately 77%. Construction of the road was carried out as per the design intent and successfully provided access for construction and operational vehicles. Inspection by the authors and the contractor indicate remarkable performance of the road after 1 year and 1 freeze-thaw cycle. The road structure as designed was able to effectively satisfy the performance requirements to prevent rutting, embankment failures, and shearing of the Muskegs upgrade. So thank you very much for listening to our presentation. We'd like to thank Eric Ludwig from Paradox for providing info on construction and performance. And if you'd like to learn more about what we do, please feel free to visit the websites listed here. Thanks for your time.